So I had why Germany, because I met this guy in Germany, the person who is going to give the talk here, and he did he studied he's from West Bengal as well, and he studied in Chandanagar. No, Don Bosco, right? So that was not in Chandanagar. Bandel, yeah, Chandanagar and Bandel is very close by. And then from there he went to St. Stephen's to study physics. And then from there he came back again to West Bengal, to Belur, to the Vivekananda University to study mathematics for his masters. And from there he did go to the Center of Mathematics and Physics, which is of the world possibly, which is Göttingen, Germany. And he did his PhD, he finished his PhD in mathematics in the University of Göttingen, finished in 2016, right, Tata? Yeah. So it's my privilege to know him personally, and I spent an extreme quality time with him in Göttingen, and it's really a privilege to be a fellow PhD students along with his time. He was 1 year senior to me, and then so we had spent fantastic time together. So he's going to give you, his name is Dr. Tathagata Banerjee, and he's going to give you an insight about his understanding of mathematics and what he thinks about mathematics, and then I hope you enjoy and then pursue thinking about mathematics as one of the subjects in future. So that's the whole idea possibly. So welcome Tathagata. So the time is around 1 hour. So you are free to decide how long you're going to spend on what. Okay?
Thank you, Sid, for the very elaborate introduction, which I'm still not very deserving to accept. So anyway, so let's get back to the talk, and also my apologies once again for the delay on behalf of the members and the organizers. So yeah, I initially planned I would be talking a lot more about my research right now, but like I would like to have you with me in the talk. So that's why I decided to make it as elementary as possible. And you are requested on my behalf and the organizers to stop me and ask questions whenever you have something that you don't understand. So I'll keep the introduction from the very basics level. So what can be the most basic object in mathematics? So that is, let X be a set. I hope everybody knows what is set means. But we can do beautiful playing around just starting from this object. So today the main part of the talk will be about, like the focus will be about playing around with a collection of subsets of a set. So you know A is a subset of X if for all A belonging to A belongs to X. So A is basically contained inside X. And now,
there is a question.
Already?
Okay, I do not know what is set.
Set is a collection of elements. Collection of
Any element?
any elements. So, I mean, here in this talk we are only considering mathematical objects. So the elements will be points or some collection of sets. That is also allowed, and things like that. But I'll be basing the talk completely on the formal set theory that is accepted, like axioms of choice and everything will hold. So I'm not going into the explanations for that, because that will take the talk to a different direction.
Just explain what is set.
Set is a collection of elements. That's it. You have to keep in mind what is a collection, like set, the collection of elements. And you have the notion of subsets of X. Now you take collection of subsets So here I is some indexing set, And A alpha, each of the A alphas are subsets of X. So each A alpha is a subset of X. And you take a collection of subsets A alpha in X. So now that can be extremely huge, right? I mean, for example, what comes to the mind? The power set of X. Right? You take any possible subset and take the collection of all possible subsets. That would be the power. So given the set X, you can talk about the power set of X. And just saying that we are considering a collection of subsets, it can be very wild. I mean, there is no control. But so we want to do something useful with this collection, right? I mean, so that it needs to have some behavioral like properties. So what I'm trying to motivate you towards, since I asked you and most of you are not very familiar with the language of topology and other things. So what I will be trying to define is a topology on X. So that would be X along with a collection tau. So tau is something like this. It's a collection of subsets A alpha inside X. Such that, so this determines this object, that is topology on X, such that the following axioms hold. First of all, this collection should contain the null set. So everybody is familiar with the concept of null set. That's the empty set. It doesn't contain anything. That will also be a subset of X trivially. So this collection should contain the null set and also the whole set X. So this is the symbol for belongs to tau. And then the second thing is, if you take U alpha, or I'll use a different index, say beta. If you take, so already you have a collection of subsets of X. Now from this collection you take any arbitrary collection. So that is again denoted by this U beta. If U beta is a collection of subsets in tau, that means this collection is contained in tau. Then union of this collection, that is beta belonging to the index set J. This will now be a set inside X, right? But for this tau to be a meaningful object, that is giving a topology on X, this union should belong to tau. So that is, which is a subset of X, belongs to tau.
Union of what and what? Sorry.
Union of these subsets, U betas. You have the collection tau.
Yeah.
Now from inside tau you have picked up a random collection, U beta.
Oh, okay. It's not subset collection of tau. It's just
it's a subset collection of tau.
Okay.
So this is the this collection is a subset of tau.
Okay.
And the union of these sets, that will be something which is not there, may not be there in this collection, right?
No.
So a priori we don't know that that union is in tau.
I mean, why would it be in? It would the union of U's
U betas
would be a subset of tau.
No, that would be a set inside, a subset of X, right? You are taking the union. So you have, say, U1, U2, two subsets of X.
Okay.
And then you take U1 union U2.
Okay.
That should also be a subset of X, a priori. But now for this tau to be meaningful, like to be a topology basically, we need that this union should belong to tau actually. For any arbitrary collection you choose, any arbitrary collection U beta inside tau if you choose, the union of the sets, that should belong to tau.
And the fact that it belongs to tau and X isn't it a given fact? I mean, like this is just like
you're defining a useful meaningful collection basically.
Okay. Okay.
That is the concept. Like you're trying to give a shape to the object, the set that you have started with. That is X. So you're starting like as in the beginning I said it, like we'll be playing around with collection of subsets today of a set. So this is a basic axiom, and another one is if U1 U2.
What is mean by topology on X? Means what
Yeah, so
does it mean?
that this tau means the topology on X. So I'm defining the object which you're asking.
Like
So it has to be defined. It is not there a priori. I mean, we have started with a set. Now we have to define topology on the set.
What do you mean by topology? What is the
Term.
So topology is okay. What do you mean in what sense? That is the question. Mathematically, this is the meaning that you have this arbitrary, a certain collection of subsets of X which follows these axioms.
Actually, topology, when I heard about it, is like study of surfaces, shape, like something like that.
Yeah. So what you have heard about is examples of topological spaces. We haven't arrived at topological spaces yet. We are still at the ground zeroth level, that is set. Once you define such a meaningful collection, you will arrive at a topological space, and then you can talk about spheres, torus,
It's not a
Klein
shape.
bottle.
It's not a
There's a
shape.
variety of objects that you can talk about. Like
So here X would be, in that example, the X would be just collection of three
So-
numbers,
so-
three
Now he's
numbers.
taking separately.
so for sphere, sphere is you have the equation x y z
Yeah,
belonging to
less than.
3 such that x square plus y square plus z square is equal to some fixed r square, right? R is the radius of the sphere.
But we are trying to arrive.
So we will take the set here will be this. So x will be this. And then, but just defining this doesn't define you a sphere.
No.
I mean, it could be this set with this point, identified with this point and things like that. That will come out from the topology. The meaning of sphere. What do you mean by a sphere? So that is